Watch and United Dynamics. OB Robotics.
Good evening. We represent OP Robotics. Today we're presenting a soft actuator. We're sponsored by the Dimensional Body Manipulators at UTSA. The key members are Juan Wang, David Alessandro, Becky Martinez, and myself, Harrison Sierra. The mentor is Dr. Hamid Zafari. This is the presentation outline. These are some of the topics that we're going to be focusing today. So a brief background on a conventional actuator. Conventional actuator has the ability to produce movement. It requires a power source, whether it's pneumatic, electric, or hydraulic. Basically, the way it produces movement is by converting energy into mechanical work. An example of a conventional actuator is an electrical power actuator that controls the locking mechanism in the door of a vehicle.
Soft robotics is a fairly new field that began in 2011. Soft robotics consists of movable, non-rigid bodies that are composed of materials that highly deform. One example is silicon rubber. Unlike conventional robotics, these are not composed of rigid, heavy metal devices like robotics. Soft robotics will have more human interaction and in the future. Components that make up soft robots are soft actuators, a large portion. And soft actuators work in the same principle that Harrison just said, in converting some type of energy to mechanical motion, electrical, thermal, pneumatic. And some applications are to help people with disabilities, so it'll help assisted muscle or mobility. Another one is as an artificial muscle on an exoskeleton application. And the last one as a neck support application on a person with paralysis to help neck mobility.
So the purpose of our project, is to design, analyze, and manufacture a soft actuator that can produce 10% displacement of the original length. With a programmatic objective, for senior design 1, we're going to design and analyze the soft actuator. For senior design 2, we're going to build it as well as test it. For analysis, we're going to analyze the mechanical system as well as its manufacturing process. We're also going to do an electrical analysis as well as a structural analysis.
So we have three essential characteristics to the functions of the actuator. The main function is to reach 10% strength. Another function is to produce a minimum 50 newtons of force, which equals to 3.3 pounds. Another one, it has to be powered by an electrical system, microcontroller, or variable voltage power supply. For the performance specifications, there's 6 components. The first one is material selection. It has to be made of an elastomer. The second one, mechanical system, 50 newtons of force has to be produced. The third one, electrical system, has to be microcontroller or power supply. Next one, adhesive Q-bond, which is elastomer has to be used. Next one, the volume, the dimensions are 80 by 100 by 160, and it has to weigh less than 250 grams. So we chose 3 different concepts. One concept using pneumatic, the next one using thermal energy, and the next one using magnetic.
Our first concept is a pneumatic soft actuator. This requires a power supply and a pump to supply air as a working fluid into the beer. Here you can see an elastomer air chamber that has embedded Kevlar threads running axially through it. So when pressure increases, this is cause tension on the Kevlar threads, which is going to cause axial compression or radial expansion. So here on this figure, this top one has low pressure, and when pressure is applied, it's going to look like figure B.
So second concept, which is the thermal expansion actuator, uses a liquid crystal elastomer, which microstructure, when you change the temperature of the microstructure, instead of expanding like most things do, it will contract. And then if you take the heat out, it will go back to its original place. If you can see the middle picture, there's 3 gray wires. Those 3 gray wires are the integrated flexible silicon heaters. The gold wire in the center of the actuator is the temperature sensor, which is a flattened cladding polymer.
So our third concept design is the electromagnetic soft actuator. As you can see on the picture on the right corner of our PowerPoint, is in exploded view using the SolidWorks. The basic part of the soft actuator, there is the outer layer, the inner layer, the embedded micro channel, the magnet, the middle traceable part, and the head cover. So each part provides a significant function for our design. For the outer layer, it will be act as an electromagnetic seal barrier to prevent the magnetic field to interfere with other electronic device. The inner layer will have the embedded coil and will be injected with conductive liquid metal. And then we have the core will be our magnet, and we have the tracker part that allow our actuator to expand and contracting, and the head cover to keep everything inside. So when the magnetic when the current is being applied to the coil will create a magnetic field that interact with the magnet, and we will bring a magnetic force that help expanding our soft actuator 10% of its original length. Because of our project is a soft actuator, the material we're gonna use is a lightweight material, which can be a conductive liquid material, soft ferromagnet, silicone rubber, iron powder. For our manufacturing process, we're gonna use a 3D printer, and we're gonna use a molding process. For our selection process, based on the methodology of how each concept works, we eliminated concept 1, which is a pneumatic soft actuator, because even though it can break more than 10% of its original length. However, it's done in a radical direction and create an unwanted displacement. Also, the force generated by the pressure is difficult to control. For our thermal expansion, the reason even though it can expand up to more than 10% of its original length, the reason we didn't choose is because of the high temperature operational, ranging from 90 Celsius up to 120 Celsius.
Why we chose this concept? Very simple. It's application efficiency. This concept can have 1 degree of freedom, and you can actually attach it to one of the exoskeletons that it wants to support, your neck or your arm. The other ones, they're not able to produce the same amount because they tend to heat up to 90 to 120 degrees Celsius. Putting that in your neck will burn it. And the other one contracts radially and axially, which will be very uncomfortable if you put it or mount it.
Here's a comparison matrix where we ranked our 3 concepts versus certain grading criteria. The lowest number is the one that we chose, which is concept 3, which is electromagnetic actuator. There's an error on the slide where it says energy efficiency. That's supposed to be application efficiency, and that was most important. The next was manufacturing difficulty, and the rest was weighted equally with weight, force, and displacement. Expected problems from our electromagnetic actuator is the difficulty manufacturing it, and that can be solved with 3D printing and our molding process. And since it's going to be used with other possible electrical devices, it has to be has to have an electromagnetic shielding around it, so it won't have any interaction with that. And the last is E-gain injection. And it's difficult to inject the E-gain into the microchannel, and this can be solved with the electrochemical capillary injection. This is the cost of most of the materials that we have, and I wanted to take a moment to thank Dr. Jafari and ArmLab for funding this and giving us the resources.
Where's the design of this thing? I don't see a design.
Internal.
That one you threw out, and that doesn't even meet your specs. That one's out. You've only got, at most, 2 concepts. The first one's not possible by your own statement. You say they had to be electric. That first one is pneumatic. So it's out. You got 2 concepts.
What number is it?
Go back to you. Performance specifications, electrical system, microcontroller, variable voltage, and all of that. Where's the electrical system?
Well,
Can you show me how you arrange your electrical channels in this device?
Which one? Which concept?
Which direction does your electrical channels go?
In this concept or which concept?
That one.
Where are the microchannels? Where's the design?
The microchannels, okay, if you can see the coil, the black circles, it's very tiny microchannel.
It's in the outer layer.
It's in the outer layer of the actuator. So the orientation, you're producing a north pole and south pole right here, and you have in the middle a soft magnet with the same opposite polarity, and the other side opposite polarity in the center of the soft magnet.
Wow, it's making